Welcome back. Let's move on in our discussion of PV system components to batteries. I will spend a few videos discussing different aspects of batteries that are important for PV system modelers and designers. This video will focus on why we need batteries in certain PV systems and the understanding of their purpose. That will be basically the learning objective of this video. In the second video, the different types of battery technologies that are currently available will be discussed. In the third video on batteries, the important parameters that define the performance and operation of a battery will be discussed as well. Batteries are an essential part of a certain PV system. You can see here that in our overview of components, batteries are part of the balance of systems. You may notice that I also include charge controllers in this slide. Since they are principally concerned with battery connected system, we will discuss them in this set of videos as well. Okay, so let's look at how a battery and charge controller are connected to a system. Batteries are typically used in off-grid PV systems. You will notice that the PV modules are connected to a charge controller. This charge controller then connects the battery as well as the inverter and DC loads. So you can see that a battery is connected on the DC side of the PV system. Basically, current from the PV modules will either flow into the battery or go to the loads. If the loads demand more current than the PV modules can produce, current will flow from the batteries to the loads as well. So why does this system really need a battery? Why can't we just power the loads with solar energy directly? One major reason is the mismatch between supply and demand. Here we have a typical solar irradiance curve throughout the day. There's a peak around the middle of the day and no irradiance during the night time. However, do we turn on all our electricity when the sun comes up and turn everything off at night? No, things don't work like that. Now in blue, a typical load demand curve is shown. This demand curve has been scaled such that you can equate the red curve to how much power a PV system can put out relative to the blue curve. You can see there are times of the day when the sun is providing more energy than is required, shown here by the green area, and times of the day when it's not of enough, as shown by the red area. An energy storage device such as a battery can assist with this. During the green period, that excess energy can charge the battery. During the red periods, the battery can output that energy that it stored during the green period. Daily fluctuations like this are one big issue. But let's take a step back to see a larger one. In this figure, you see the load demand curve for a whole year instead of one day. The x-axis shows our time in months. Now in blue, you see the corresponding irradiance curve for those 12 months. You can see that in the summer months we have a lot of extra energy, which is shown by the green color, while we do not have enough in the winter months, which is the red area in the figure. This is known as seasonal mismatch of a PV system. You need some type of energy storage to solve this mismatch. If you were to make the PV system large enough for the winter, then the system would be huge and would not be cost effective. Additionally, you would waste a lot of energy in the summertime. Therefore, if you have an electricity system that is totally dependent on PV, you need some storage that can handle these seasonal fluctuations. Unfortunately, batteries are not cost effective to store this huge amount of excess electricity in summertime. A more promising example for seasonal storage would be the generation, storage and consumption of green hydrogen. So we have daily fluctuations that require energy storage, which can be in the form of a battery. You can also probably imagine that the PV power production doesn't always look as smooth as that red curve due to clouds passing by overhead. A battery will help with this as well. However, there is another reason why an off-grid system needs a battery. This is the voltage of the system. You are well aware by now of the IV curve of a solar panel. You also learned that if we connect a solar panel directly to a load, it will change depending on the demand of the load, and this will be very difficult to control. Batteries, on the other hand, are quite easily simulated by a constant voltage source. This essentially defines the system voltage. There might be subtle changes to the voltage, but a battery acts as the bedrock for the voltage of an off-grid system. This is not the case for a grid-connected system, because in those systems the grid itself supplies the stable voltage. In summary, batteries are used in PV systems to overcome the mismatch in solar electricity supply and electrical consumption in timescales of a day or smaller. In addition, in standalone PV system, the battery component delivers the stable voltage of the PV system. In the next video, we will discuss the most common battery technology. So see you in the next video.